Hi, so today I want to talk about the code that makes the 8088 or 8086 that's plugged directly into the Raspberry Pi 40-pin pin header. So this is the library I wrote. This is the kind of like the core of what makes it work. So here's the header file. So we described each pin. You can see the address, data, address. Obviously these are address data for the V30, but I never changed it. It's just how it is. And then we've got our public functions here. But internally, so we've got our RAM described here in a array, 1 megabyte, and we have our I/O here, 64K. Then here's the function. So to read the address, it'll just read each pin and shove it over and add it up, and then returns the address. Read the control bus. You got to read, right, I/O mem. Read your memory bank. This is for the V30, 8086. And then down here, this sets your port direction. So if you're using the 8088, you tell it in, they're all in, out, they're all out. So the address, the ones that are address only, never change direction. This is just your data port. And then down here, the 8086, you're going to do all 16 lines, in or out. And then write data to the port. There's your 0s through 7, 8 through 15. And then data port. This is read from data port. And then you got your high and low as well. Here's the clock. So if you put a delay in there, it was almost like way too long. Like if it did like a you sleep or a sleep. But by just writing to the pin, it created just enough delay. And I've added and deleted of these a few times. And this particular combination right here, the enough highs and lows, seems to be the most stable for both processors. The V20 can actually go a little bit faster, so you can remove one or two of the highs. And like I said, these are just for a delay. You could write to anything, really. So then the initial setup, we set up wiring pi, the stop flag faults. That's used to keep our loops going. Everything's an input here on the address bus. The click and the reset are out only on the control bus. So, and then this is really the heart right here. So this is the system bus. It runs in a loop, and it determines which processor. And that, let me just show you real quick. When you start your processor here, you type in which one you want. And so then it just deciphers which one you're going to do. And here's the 8088, which is going to be more simple. So it clicks, reads the ALE pin. If it's high, it grabs the address. If not, it goes down here and it reads the control bus, and then it determines. So 01 is a memory write, 02 is a memory read, and then down here we've got our, this one is actually not set up for the I/O ports yet. I've done more development on the 8086 side. I mean, it's just a matter of just copy and pasting and changing a few numbers here. Right here at the bottom, I put in this at the previous control bus. So this saves it to this just character here. And then it says if the control bus is not the same. This way it doesn't just sit and repeat and do the same thing. Because there's actually 2 clock cycles when you try to read and write. So this just makes it so it only does it once. It just helps speed things up a little. And so then it just loops. And then here's your 8086. So it starts out the same way, but it also reads the memory bank. So that you can determine if it's both high and low, high or low. And then it comes down here. Same thing, it checks to see if the control bus is the same. That way you're just not double doing things. And then right here. So if you notice, the right here for memory is a 5, but up here it's a 1. The reason being is the memory I/O select pin on the 8086 is actually inverted. So it's high for memory, low for I/O, where on the 8088 it's the other way. So then it comes down to your memory bank. If it's 2 zeros, then it's both. If it's 1, it's the high. If it's 2, it's the low side. And then you use the same byte array. So instead of having two, like a high and low bank of RAM for the 86, I can use the same RAM. You just tell it high or low, odd and even, basically. And that's why here you can see 8 through 15 goes into address plus 1 because that's an odd address. But when it's reading the directly here, you don't address plus 1 because it's going to give you an odd address to start with. So here's the read. And then down here I actually did the IOs for the 8086. And you can see I put in some printf stuff here so that it would print to the terminal. And it would tell me which ports were trying to be written to or read from. It's all commented out right now, but just up for debugging. So then you got your write, and then it comes down here. And then saves the control bus to the previous, and that way it doesn't redo it. You can see it's really, really simple. It just clicks it, sees what it wants, gives it what it wants. Clicks it, sees what it wants, gives it what it wants. So anyway, so down here I've got some functions. Write memory array, read memory array, write byte. And this is just to interface with the window here. You can see like it's going to read the memory array. That's how like when you load your BIOS. Now you could we could just make this public and just have it so that you can read and write directly to RAM. But this kind of just makes it in a function. Down here you got your reset. So it holds the pin and then it clicks 4. You have to click 4 times to reset, but I clicked 8 just to guarantee we do every time. Here's the start, and this is where you put in your processor. It sets it up, resets, and then it starts the system bus, and then it detaches the thread. So, and then down here you've got your how you load your BIOS. It just opens the file. So that's the basic file that makes this whole project work. So I encourage you to download the project and try it out for yourself and see if you can make it run. The big thing is if we can get it run faster, so that it's like this here. I mean, it's fairly slow. The thing is, let me show you it running here. You can see that it's going to boot up fast and it's going to load DOS really fast. But that's because when you're reading from the drive, like in the old days, you'd be taking forever to read from your drives. But it's virtual, so it just loads the drives really fast. But then when you run programs, so like, we'll just do this there. You can see, I mean, that's going across pretty fast. And that's actually the speed of that writing that across the screen is off the timer. So if I actually speed up the timer, it will, it'll actually go faster. But you can see it's playable, but it's definitely slow. And you can't see the bullets because of the BIOS interrupts for the screen aren't perfected yet. But they're there. You can see that the guys are getting hit. But let me show you the timer really quick. That's kind of important. So all it does is ticks, and then I did some math. It's supposed to click like 18.2 times a second. So that's kind of like that sleep is about that, at least according to the math. I mean, that's not accounting for the loop time or anything like that. And then all it does is updates the byte at 46C and 46E. Well, actually, it's a double word, so it updates those 4 bytes. Same thing, it's got a system to start down here, and that's just another thread that just attaches. And you can see that it includes the, in the header file, we include the x86 header file, and so it uses that stop flag. So once you, like here in the main file, once you tell the stop flag to be true, it stops and all the threads stop. So there you go, a real basic look, but I just mainly wanted to show you the x86 library that makes it function. So thanks for checking it out.